Welcome to G Fun Facts Online. Imagine holding a beam of light like a pliable thread and then tying that thread into a knot. This isn't science fiction. Scientists can now tie light into knots, creating stable three-dimensional structures of darkness inside a luminous field. These optical knots are unlocking revolutionary possibilities, and today we're going to unravel exactly how and why. So how do you tie a knot in something that has no substance? The key ingredients are features called optical vortices. Think of a vortex as the calm, dark eye of a hurricane made of light. Around this dark core, the phase of the light wave twists like a corkscrew. This twisting is quantized, meaning it comes in whole number steps. A topological charge of +1 means the wave twists 360 degrees clockwise in one wavelength. -1 is counterclockwise. The dark line at the center of this twisting vortex is called a phase singularity. These lines of pure darkness are the threads physicists have learned to braid. This twisting motion also gives the light beam a special property: orbital angular momentum. This is different from the spin of light you might have heard about. This orbital momentum can be transferred to matter, allowing these beams to act like optical spanners that can grab and rotate microscopic particles. But the real magic is topology. In mathematics, a knot in a rope is still a knot no matter how you stretch or bend it, as long as you don't cut it. Optical knots have this same topological protection. The simplest non-trivial knot is the trefoil with 3 crossings. Next is the figure 8 knot with 4. Physicists have created these and even more complex structures. This mathematical robustness is what makes them so powerful. Amazingly, the idea of knotted fields is over 150 years old. In 1867, the famous physicist Lord Kelvin watched a demonstration of smoke rings. He was struck by their stability and how they interacted. This sparked a radical idea. What if atoms themselves were just knotted vortices in a hypothetical medium called the luminiferous ether? He thought different knots could represent different elements. A simple ring for hydrogen, a complex trefoil knot for carbon. This theory, though wrong, inspired his colleague Peter Tate to start classifying knots, accidentally creating the mathematical field of knot theory. The vortex atom theory eventually died out after experiments failed to find the ether. But the mathematics it created lay dormant for a century. The idea was reborn not in a mythical ether, but in the solid equations of electromagnetism formulated by James Clerk Maxwell. It turns out that knotted configurations of electric and magnetic fields are perfectly valid solutions to Maxwell's equations. Kelvin's dream was right in principle, just in the wrong medium. Creating an optical knot today is like digital weaving. The heart of the operation is a device called a spatial light modulator, or SLM. It's essentially a high-resolution computer screen for light. Scientists first design the exact knot they want on a computer. Then they calculate a special pattern, a hologram, that needs to be displayed on the SLM. A simple laser beam is shown onto this SLM. As the light reflects off it, the hologram pattern is imprinted onto the light's wavefront, sculpting it. This modulated beam then passes through a series of lenses, which causes the light to interfere with itself in a precisely controlled way, forming the desired three-dimensional knot in space. But how do you see a knot made of darkness? You can't directly. Instead, scientists use interferometry. They combine the knotted beam with a simple, flat wave of light. The resulting interference pattern reveals the phase structure, showing a complex web of branching forks that trace the path of the dark vortex lines, allowing them to reconstruct a full 3D image of the knot and confirm its topology. This is where things get really exciting. Because different knots are topologically distinct, they can be used to encode information. A trefoil knot could be a 1, and a figure-8 knot could be a 0. The knot's robustness means this data could be sent through turbulent air or water with fewer errors. Add a twist to the polarization field around the knot, creating a framed knot, and you can encode even more information, creating a potential basis for ultra-secure cryptographic keys. These knots are also poised to revolutionize microscopic manipulation. The complex light patterns can act like 3D tractor beams, trapping multiple particles and moving them along prescribed paths, like a microscopic assembly line. The built-in orbital angular momentum can also be used to spin these particles, creating optical spanners to assemble tiny machines. The knot's structure can also be used for sensing. While topologically stable, a knot's geometric shape can be distorted. By sending a knot through atmospheric turbulence and measuring how its shape deforms or even breaks, scientists can precisely measure the strength of that turbulence. The knot becomes a sensitive 3D probe of its environment. The future of this field is even more mind-bending. Researchers are now designing space-time crystals made of light, where knotted structures called Hopfians repeat in a lattice through both space and time. This could lead to incredibly dense new ways of storing and processing information. But the ultimate prize is topological quantum computing. Most quantum computers today are plagued by errors because quantum states are incredibly fragile. A topological quantum computer would encode information in the global topology of a system, like the braiding of particle world lines. Because the outcome depends only on the knot-like structure of the braid, it would be immune to small, local errors. Knotted light offers a potential pathway to realize these ideas, using the topological features of light to create robust, fault-tolerant qubits. This is the Holy Grail, a quantum computer that protects itself from errors using the fundamental laws of knot theory. So, from Lord Kelvin's flawed 19th century vision of vortex atoms, we've arrived at the cutting edge of 21st century physics. We've learned to treat light not just as a wave or a particle, but as a building material we can weave into intricate, robust structures. The key is topology, encoding information in the global shape of a knot, making it resistant to noise and disruption. This opens a new paradigm for everything from secure communications and microscopic robotics to the very architecture of future quantum computers. We are just beginning to unravel this unseen tapestry of light, and it promises a future that is anything but straight and narrow.